we've seen a variety of functional groups up to this point: alkenes and alkynes, alcohols, ethers. Let's take a moment and do some review problems where we can bring them all together and tackle some problem-solving strategies. We're going to focus on the transform type problems, the synthesis problems, because these are the ones you typically don't have too much experience with and are very challenging and are a step above the more simple predict the product type problems, which you probably do get a lot of examples to work through. So here's our first one. Let's say we wanted to start with this alcohol and go to a Grignard reagent, and the approach we're going to take for all these transform problems is we're going to look at our product and analyze that product, do a retrosynthesis. Every time we do this special retrosynthesis arrow, it asks, what starting materials do I need? In other words, we need to imagine the reaction that can be used to form the product given. And so what that requires is a functional group analysis. We take a look, we see that this is a Grignard reagent, and then we have to go back and ask, well, we've made Grignard reagents before. How did we do that? Where did that come from? We added magnesium metal, and what was there in the first place? The halogen was there in the first place. So in other words, you need to start with a halide to do to form a Grignard reagent. So by working backwards a little bit, we can come up with a structure that hopefully we can get to in the forward direction from the starting material that we're actually given. In this case, we're given an alcohol. And so what we would need to do is convert this alcohol to an alkyl halide, and then we would be convert the halide to the Grignard. So, you know, a lot of these transform type problems, multiple step transform type problems, all come down to finding this key intermediate structure, one or two structures that you can both get to from the starting material and go from to the product. And it helps by working backwards a little bit, working forwards a little bit, and hopefully meeting somewhere in between. So both of these are transformations we've seen before. We've seen that we can go from an alcohol to an alkyl halide. And actually there are quite a few possibilities for that. One possibility would be something like HBr. Okay, but the problem with a strongly acidic HBr reagent is it very much favors carbocation formation, and because this is on a primary carbon, and right next to it we have this benzylic carbon, it's far too easy for a rearrangement to occur and for the bromine to end up in the wrong position. Okay, so that's probably not the best strategy. And instead, we want a strategy that's going to not have a chance of rearrangement. So maybe a reagent like PBr3 would be better, because that would make the bromide exactly where the OH used to be, and so there's no chance of rearrangement there. Maybe you could also, to count on an SN2 reaction, you can do the tosylate. You can make tosyl chloride pyridine to make the tosylate, make the OH a good leaving group. And then step 2, you can add in sodium bromide to do an SN2 on that good leaving group. That would be another strategy where there's no chance of rearranging and the bromine exactly replaces the OH wherever it used to be. Okay, so either of those reagents are fine, and what you'll find is many of these transform type reactions, there are multiple possibilities for a correct solution, either sometimes in strategy, but most definitely in the reagents that you choose. Okay, and then how do we go from the alkyl halide to the Grignard? We simply add in magnesium metal. Sometimes you'll be, showing you. Sometimes you'll see this with the solvent as well, but just the magnesium is that's definitely the most important part. Okay, how about our next one? We need to transform. We're starting with an alcohol, and we're going to an ether. Okay, so if I want to do and we also notice that there's some stereochemistry that will be relevant. Our oxygen was on a wedged bond, and our oxygen this oxygen is also on a wedged bond, so we're going to need to take that into consideration when we come up with our strategy. Okay, but let's consider our retrosynthesis and ask what starting materials do we need. And we consider our functional group that we have in our target molecule is an ether. Now, how do we make an ether? We need two ingredients. We need an alkoxide and an alkyl halide. We need to do a disconnection, and we can either do a disconnection on this side of the oxygen or this side of the oxygen. Now, if we were to form this carbon-oxygen bond as our new bond, that's going to it's definitely going to have an effect on the stereochemistry of that bond. And since the stereochemistry is set and we want to keep it fixed, let's avoid that bond and let's look at this disconnection instead. In fact, this is even the better disconnection because this leads to a carbon that is less sterically hindered. So we're going to break this bond. The oxygen was our nucleophile. The carbon was our electrophile, and that's how we come back to our alkoxide nucleophile. And an alkyl halide, the way we make this carbon electrophilic is we add on a halogen. Fluoride, chloride, bromide, iodide, your choice. I'm sorry, not fluoride. Chloride, bromide, iodide is your choice. So alkyl halide would be our electrophile, and when we combine an alkyl halide and an alkoxide, we call that the Williamson ether synthesis. And that's going to be a very good way to synthesize ethers. Not the only way, but one of the ways that you should probably consider first. Because this now is a strong nucleophile, we expect it to do an SN2, and that will definitely give us our target molecule. Okay, so this is what we need. We need this alkoxide and this alkyl halide. We come back to what we have. We have this alcohol. So how do I convert an alcohol to an alkoxide? Looks like I just have to deprotonate that hydrogen. We have to deprotonate the alcohol. So what kind of reagent will do a deprotonation? A base, a strong base. How about sodium hydroxide as a strong base? Would that completely deprotonate my alcohol to give an alkoxide? No, that's not a strong enough base. That's too similar in reactivity to the product you're trying to form. So we learned about two other reagents that would be better for this. We could use either sodium hydride, which would be an irreversible reaction that gives off the hydrogen gas, or we could use sodium metal, sodium 0, and that would do a redox reaction to do that same reaction. So either of those reagents is fine. Just pick one and go with it. And once we have our alkoxide, we would then throw in our ethyl iodide or iodoethane and do our SN2. At this point, you make sure you ask yourself, is this a good SN2? Would that work? We have a primary alkyl halide, so that's the perfect kind of SN2. Remember, this is a very strong base, so we can't do an SN2 if it's secondary or tertiary. We want to make sure that, and that's part of the decision we make here. If both of these disconnections were possible, then we would use a steric hindrance of the potential SN2 as the way to guide which one is the better disconnection. How about this one? We're starting with an alkyne, and we have both of our double bonds are gone, and we now have a diol. We have two OHs in our structure. We also have a particular stereochemistry shown where this is a wedge and this is a wedge. Okay, now when we do a retrosynthesis on this, we ask what starting materials do I need to give this product. Now, have we ever seen a reaction that gives as a product a structure with an OH on each carbon? What starting material did you have for that? You started with an alkene. If you did have an alkene, we could do a reaction that made a diol. You remember this one? What kind of reagent do we do for that? That was an oxidation. That was KMnO4. So just a little reminder here of the problem solving you need to think about. We need to remember the reaction that we saw, what reagent was it, and more importantly, what functional group did it start with, so we could do our retrosynthesis. Now tell me about the stereochemistry of that dihydroxylation. Remember, the KMnO4 or the osmium tetroxide delivered both oxygens from the same face. We call that syn addition. Okay, so before we plan what starting material we need, how about rotating this around so that we see the syn see it with the OH group cis to each other coming from the same face. So this right-hand carbon we haven't rotated, but this left-hand carbon we rotated the OH up 180, which takes the ethyl group that was pointing toward you and moves it to be pointing away from you. So this is a better way to view that molecule, because now you see that if you wanted to do syn dihydroxylation, you get this product, and what starting material would it have come from? What is the stereochemistry of the alkene that you would need initially? You see how the methyl and the ethyl group are trans to each other? Well, that's the stereochemistry we need in our starting material. You can verify this as doing it like a predict the product. If I had this alkene, would it give this product in dihydroxylation? Sure, the OHs come from the same face, and the trans relationship of the ethyl and methyl are seen in the product. Okay, so that helps us get the stereochemistry right. How do we go from here to here? How do we go from a alkyne to a transalkene? Have we seen that transformation before? It is a partial reduction of the alkyne. We call this dissolving metal reduction. If we use sodium metal and NH3, liquid ammonia, we do a dissolving metal reduction, and we go from the alkyne to the transalkene. Once we have the transalkene, how do we go to the diol target molecule? We add in our KMNO4. So this not only changes the functional groups that we want, but it also gives us the proper stereochemistry. Now, one other thing to consider, another possibility, is have we ever seen a reaction that adds two OH groups to the opposite face? We have. What if we did it via an epoxide intermediate structure? If we had an epoxide, one oxygen would come from the top face and the new oxygen would come from the bottom face. And so let me redraw this so we can see it again. What if we wanted to do an anti-dihydroxylation? What alkene would we need to get the stereochemistry that's shown here? Now these are already drawn in the anti relationship, the trans relationship. So this has the ethyl and the methyl in the same, on the same side. So if we had them cis to each other and then we did an anti-dihydroxylation, that would successfully give us our target molecule. So another possibility to get this same target molecule is to reduce this not to the transalkene but to the cisalkene. And how do we do that? Dissolving metal reduction gives the trans. To get the cis, we need to do catalytic hydrogenation. Okay, but we can't just do plain catalytic hydrogenation because that would get rid of all of our carbon-carbon pi bonds. So instead we use Lindlar's catalyst. And that is our poison catalyst that stops at the cis-alkene. So we know how to get the cis-alkene. How do we then go to the target molecule with the proper stereochemistry? How do we do our anti-dihydroxylation? Well, we want to make an epoxide and then open up the epoxide. This can actually all be done in one pot. If we use peracetic acid as our epoxidation reagent, and we do this in water, this makes the epoxide, and this opens the epoxide. And so this is a one-step process for doing anti-dihydroxylation, where you add two OHs and they come from the opposite face. Syn hydroxylation, because it's a concerted mechanism with KMNO4. Anti-dihydroxylation, because we're forming the epoxide and then we're opening it up. So if you don't remember that we can do this all in one step, you can also do it stepwise. We could say, okay, step one, let's make the epoxide. What oxidizing agent does an epoxidation? We need some kind of peroxy group like MCPBA. And then we can follow that up after we make the epoxide. Then we can, here I can draw this out so you could follow along. We could react this as MCPBA. We should make the epoxide with the two groups syn to each other. Cis to each other, and then we can open that up with water. We could either do that with basic conditions or acidic conditions. Let's say NaOH water. For example, that would open up the epoxide ring with hydroxide, and we would get our two OHs coming from in opposite directions. Okay, remember this is racemic, so I've drawn just one enantiomer here, but both enantiomers would be formed And so when we open this up, we would get both enantiomers as a possibility. Okay, so we could either do one step with the peracetic acid or two steps with MCPBA followed by NaOH, H2O. Okay, so a few different ways to get this particular stereochemistry, and these both options are possible because we know how to go from the alkyne to either the cis or trans alkene, and we also know how to add two OHs either with a syn mechanism or with an anti mechanism. So that's why we get two possible routes here. Okay, here we have another ether as our target molecule. So when we think about how to make an ether, we need to do a disconnection from one side or the other of our oxygen bond. When we're doing a Williamson ether synthesis, we want to, our oxygen is going to be our nucleophile always as an alkoxide. But when we consider our possible electrophiles, we want to have an electrophile that has the least steric hindrance possible. Okay, so this electrophile is a better one because it's just a methyl group. So we'll do that disconnection instead, which means we need this alkoxide plus this alkyl halide. That's our two ingredients for the Williamson ether synthesis. RO minus is our nucleophile, and RX is our electrophile. Okay, just very briefly, why didn't I make that other choice? The other possibility of having chloride, bromide, iodide, whatever you have here, and methoxide. If you wanted to do this Williamson ether synthesis, because this is a secondary alkyl halide and because this is a strong base, we're not going to get the SN2 as a major product here. These are going to combine to do the E2 elimination, and we're going to get the alkene product out. So guess what? All that hard work, we would go back to our starting material. We don't want to make the alkene, we want to make the ether. Okay, so this is the best SN2 on the methyl iodide. And so we need this alkoxide. Where does an alkoxide come from? Once again, I'm going to ask, what starting materials do I need to make this alkoxide? Where have we seen alkoxides come from? Well, instead of where we had an O minus, we needed an OH. If we had an OH there, then we could convert it to the alkoxide. Okay, so I think our plan is coming here. We've done our planning. We've thought things through. We have an alkene. Now we need to get to this alcohol. So that looks like we added an OH. We also added an H here, just so you can kind of see the difference. We need to add an H and an OH to our alkene. So that looks like a hydration reaction. How about using H3O plus? Would that give the proper regiochemistry? How would you describe the regiochemistry? We want to add water. Just a little note here. And our regiochemistry, our hydrogen goes to the carbon with more hydrogen, so we get Markovnikov regiochemistry. So H3O plus would do that. Okay, but what mechanism do you have with H3O plus? We protonate the alkene, we get a carbocation. That carbocation is free to move. Now, it's not going to have a big driving force to move because we would go from a secondary to another secondary, but it certainly can move and will move, and we'd probably get a mixture of alcohols. So a better reagent for adding water with Markovnikov regiochemistry, the better strategy in the lab, if there's a possibility of getting more than one alcohol product, is to do oxymercuration reduction. So those reaction conditions are as follows. Mercuric acetate, HGOAC, taken twice in water. So we do our oxymercuration. We add mercury and oxygen that first step. And then step 2, we do some kind of reduction, demercuration. Sodium borohydride does that, replaces the mercury with a hydrogen. So oxymercuration, demercuration, or oxymercuration reduction does exactly this. It adds water, and it gives it with Markovnikov regiochemistry. Okay, very good. How do we convert this alcohol to an ether now? This is similar to one we just saw. We need to deprotonate completely, so we can use something like sodium hydride to deprotonate completely. Sodium metal would work fine here too. Again, your choice to pick any reagent you want. If there's more than one choice, that will work. Okay, we make the alkoxide, And then we add in our alkyl halide. We wanted the methyl group. Remember, methyl iodide is the one methyl halide that is a liquid rather than a gas, so that's the one that's better in this case rather than using a bromide or a chloride. And we make our ether. Very good. Okay, our next one is interesting. We have a 4-carbon chain and another 4-carbon chain, so we haven't done anything to that. But we now have a carbonyl. And there have not been many reactions we've seen that give carbonyls as a product. So again, let's think back. And we haven't really talked about synthesis of carbonyls yet. We will be doing that a little later when we're talking about aldehydes and ketones. So let's ask, what starting materials do I need? What reaction have we ever seen that gives a carbonyl as a product? We've seen ozonolysis, okay, that would break our carbon chain apart, and we want to keep all our carbons here, so that's no good. What other oxidation reactions? A carbonyl is pretty highly oxidized, so it has 2 CO bonds. What other oxidation reactions have we seen? How about if we had an alcohol? Can an alcohol be oxidized to a carbonyl? That was one of the oxidation reactions we studied. So, so that would be a way to make the carbonyl. And that would be something we could get to from the chloride. So let's try our transformation. How would we go from a chlorine to an OH? Looks like some kind of substitution reaction. So we have a choice. Do you want to do SN1 mechanism, SN2 mechanism? Well, no, stereochemistry is shown. That's not an issue. But how about our carbon bearing our leaving group? This is a primary alkyl halide. We have a primary leaving group. Is that better for SN1 is carbocation. SN2 is backside attack. Which one is better for a primary leaving group? Absolutely SN2 is great because there's no steric hindrance, and the carbocation would be awful if it was primary. It would be guaranteed to rearrange. So we definitely want an SN2, so that means we need some kind of strong nucleophile. We need an OH that's a strong nucleophile. All we need is hydroxide. NaOH. We'll do a SN2 here because it's a primary alkyl halide, so we have a good yield of that. And once we have the alcohol, we're going to oxidize this to the aldehyde. We've seen a variety of different oxidation reactions, Jones, PCC, Swern. Which of those, if any, would be suitable here? Can we use any one of them, or do we have to be careful in this case? Well, remember, this is a primary alcohol. So if we were to react with a very strong oxidizing agent like Jones conditions, sodium dichromate and acid, chromic acid oxidation, that would oxidize this carbon not just up to the carbonyl, but all the way to the carboxylic acid. Okay, that would not give us the product we want. So what oxidizing agent gives us just the aldehyde? Well, those are the other two, PCC or Swern. Swern has a whole laundry list of reagents. So when I'm doing a synthesis problem and it's my job to pick a reagent, guess which one I pick? PCC, because it's so much easier and so much shorter. And PCC stands for the reagent pyridinium chlorochromate. So this is something you could actually go to the stockroom and say, hey, can I have some PCC? So, so this two-step transformation looks pretty good. The nice thing about these transforms is when you're done, every step should be a reaction you've seen before, should be something that you can predict the product and verify that the transformation is a valid one, okay? I realize, and that's the frustrating thing about transforms as well, because once you see the solution, it seems so simple and you think, how could I not have seen that from the very beginning? But of course, when we're looking at a blank piece of paper, it is very challenging. That's why it's really worthwhile to go through these examples. Okay, so speaking of that, here's our blank piece of paper. What is our simple solution? Okay, again, here's our product. I want you to think about that product. Think about the functional group in that product. Ask yourself in this retrosynthesis, what starting materials do I need? What reaction have I ever seen that gives this functional group as a product? How would you describe the functional group? It's an epoxide. So what reaction have we seen that gives an epoxide as a product? And what functional group did we start with in that case? Well, we started with an alkene. If I had this alkene, I could epoxidize it to the epoxide. I could oxidize it to the epoxide. Okay, so this looks like I just need to make this alkene. We're starting with an alcohol, and we've seen that transformation before. We've seen conversion of an alcohol to an alkene. For example, we have something like H2SO4 heat. Right? We did dehydration is a way to lose water from an alcohol. But before we think we've solved this problem and move on to the next step, let's treat it as a predict the product and ask, will this work? If you were to dehydrate this alcohol by something like H2SO4 heat, what product would it give you? Remember Zaitsev's rule? Zaitsev's rule states that you get the most stable alkene product possible, especially in a dehydration and where you have a carbocation intermediate and the carbocation can move anywhere it wants. So for sure we would get the tri-substituted alkene as our major product. Okay, so that's not going to work in this synthesis. So how can we force the elimination over in this direction when eliminating over here would clearly give them more stable alkene? Well, if we're trying to do an elimination, remember we have two mechanisms to pick from. It can either be an E1 elimination or an E2 elimination. Okay, and before you select your reagents, you need to think about which mechanism is going to work in this case, or which one is better. Sometimes it doesn't matter, but this is a case where it really does. If we did an E1 elimination, introducing a carbocation, guaranteed we're going to eliminate to the right and get them more stable alkene product. Okay, how about if we did an E2? Why would an E2 elimination not give the same product and not give this tri-substitute alkene? Well, do you remember about the stereochemistry of an E2? Remember an E2 is the one-step mechanism where you attack the beta hydrogen, form the pi bond, and kick out the leaving group. Okay, do you remember anything about the stereochemistry of the leaving group and the beta hydrogen? What stereochemical relationship did they have to have? They had to be anti to one another. This is anti-elimination. So if we were to do an anti-elimination here, there's no if the OH or whatever leaving group we have is a wedge, the only anti-hydrogen is over here, and so that needs to be is the only place that you can do an E2 elimination. Okay, so I think we figured out how to handle our regiochemistry. So how about if we just treated this with TB-toxide? E2 elimination, we do TB-toxide, strong bulky base, throw in some heat. How does that work? That doesn't work very well. What's the problem? We have a strong base, grab the proton, form the pi bond, kick off the leaving group. There's no leaving group. An alcohol is not a good leaving group. We can't do an E2 elimination with an alcohol. We can only do the dehydration E1 elimination. So if we need to do an E2, we need to have a leaving group. So what we're going to do instead is we're going to convert this into a leaving group. We need to keep the stereochemistry so that this is still a wedged bond. So what leaving group can we turn OH into where we would retain the stereochemistry? How about making it a tosylate? This is a perfect situation for a tosylate because it doesn't affect this carbon at all. It just changes adds the tosyl group onto the oxygen. So if I did tosyl chloride and base, like pyridine, tosyl chloride, pyridine, makes the tosylate. Now TB-toxide and heat, if you want, really any base. Sodium hydroxide would work here. Anything would work because it's secondary. Any base. Even sodium hydroxide and heat. Okay, this would favor the E2 elimination. It has to go in this direction to do anti-elimination. And then how do we convert this to the epoxide? What's our reagent for the epoxidation? Some kind of peroxide reagent. MCPBA, again, is typically a favorite because it's easy to remember and works very well. It's very commonly used. Okay, that was a difficult one. Lots going into that one. Okay, how about our next one? Here we have as a target molecule an alkyl halide. We have an alkyl halide. So we need to think, when we do our retrosynthesis and ask what starting materials we could have started with, we need to think about what reactions have we seen that give alkyl halides as products. Okay, well, we've seen examples where we've added HCl across a pi bond. That would be a way to introduce a halogen to our molecule, right? We could have an alkene plus HCl, for example. Another way to make an alkyl halide is maybe we could have an alkane plus Cl2 and H-nu. Do free radical halogenation. That's a way we've seen to make a halide. What's another way? We saw that if you have an alcohol, we can convert that to an alkyl halide either with HCl or with SOCl2, right? So a few different choices here. We can use a double bond or even just an alkane or an alcohol. Which of these syntheses would be best in the given situation? Well, now we look to see what starting material given. We're actually given an alkene. So we want to add HCl. Can we just add HCl? Would that work? Is it that simple? Let's predict that product. If you predict the product, you break the pi bond, you add an H and a Cl, you add one thing to each carbon. Where does the hydrogen go? Hydrogen goes to the carbon with more hydrogens. Remember Markovnikov's rule. So that won't work because we want anti-Markovnikov. We need anti-Markovnikov. Okay, well, how about, hey, I saw this trick before with HBr. How about if I did HCl but in the presence of peroxides? Would that then initiate a radical mechanism and cause anti-Markovnikov addition of HCl? Unfortunately, no. This is for HBr only. This is for HBr only. So we can't do that for the chlorination reaction. Okay, so instead, I think we're going to want to go through this route and say, well, let's put an OH group here first. And if I had an OH here, then I can convert that OH to a halide, to a chloride. Okay, so let's fill in our reagents here. Now that we've done our retrosynthesis and our forward synthesis a little bit, let's fill in our reagents. We want to add water across a pi bond with anti-Markovnikov regiochemistry. So this is a reaction we do know how to do. That's hydroboration oxidation. So BH3THF. Hydroboration oxidation is H2O2 NaOH. Adds an H and an OH and adds it with anti-Markovnikov regiochemistry. No stereochemistry is shown here, so that's not relevant. And then how do we go from an OH to a Cl? Once again, if we tried to use HCl right next to this tertiary carbon center, very likely to get rearrangement with a carbocation intermediate. So strong acids are difficult because they really favor carbocation formation. So a better reagent would be SOCl2 because that directly replaces the OH with a chloride. No chance of rearrangement. Okay, just a few more. Let's think of this one. We have an ether that we want to make. We have an ether. How do we make an ether? Well, we could do a Williamson ether synthesis. So we could disconnect here, or we could disconnect here. You know, I'm wondering we could maybe we can do this probably. We could disconnect in either direction, and because these are both primary, they will both work. So this is a reasonable possibility in either direction. Okay, we can maybe look at both syntheses. Either we have this is our alkyl halide and this is our alkoxide, or this is our alkoxide and this is our alkyl halide. Both of those would be totally reasonable syntheses because they're both primary and they would both give good yields of the Williamson ether synthesis. So we either want to put an oxygen at this end carbon or a bromine at this end carbon, but both of these are going to be anti-Markovnikov once again. So we could either do that with the bromine by doing HBr and peroxides. And then we can treat this with sodium ethoxide to do our SN2. So that would be a simple way to do it. Or we could do anti-Markovnikov addition just like we did before. of water with hydroboration oxidation, BH3THF, H2O2 and base. That's anti-Markovnikov. And then to go to the ether, we have to take our alcohol, we have to convert it to an alkoxide. And so that means step 1, we're going to use NaH to make the alkoxide. And then step 2, we can put in our alkyl halide, ethyl bromide. Very good. Okay, and let's look at one more example here. We have another transformation. Looks like we have an alkyl halide. We just talked about some of the options that we have for put a halogen in the structure. We could start with an alkane, we could start with an alkene, we could start with an alcohol. Okay, but here when we look at our starting material, we say that we're starting with an epoxide. And so we already have an oxygen in the structure. So I think this is going to be one of the examples where our simplest synthesis is going to be where that alkyl halide came from having an OH in our structure initially, and then we convert it to a Br. Okay, so now we have this alcohol we need to make. We're starting with an epoxide. There were 2 carbons in the epoxide. These are the 2 carbons that are still here, so this phenyl group clearly wasn't there in the starting material. We have to come back and add in that phenyl. So one of these groups was my nucleophile, one of these groups is my electrophile. In order for them to come together, let's think about the carbon as it was in an epoxide. What kind of reactivity do we have for an epoxide carbon? This is partially positive, so it is an electrophile. So what we need is a phenyl. So this carbon was my electrophile as the epoxide. And what we need here is for the phenyl to be a nucleophile. How do we make a phenyl group nucleophilic? It's like if I had a phenyl minus, for example, that would be good. That would be a good way to open up the epoxide. How do we get a phenyl minus? We use an organometallic reagent like phenyl magnesium bromide or phenyl lithium. Those both work great, a Grignard or an organolithium. And that's how we're going to form this new carbon-carbon bond. So let's do our synthesis then. We've already started the epoxide, so now we'll add in phenyl magnesium bromide. Okay, that can't be our complete reaction though, because our phenyl minus would open up the epoxide ring. So we have phenyl minus opening up the epoxide ring. That would form this bond, but it would give an O minus here. So every time we use a Grignard, it's always a 2-step process. Step 1 is the Grignard or the organolithium, and then step 2 is H3O+. You always need this aqueous workup to protonate the O minus that you form in that first step. Okay, that's going to give us an OH and a phenyl. So my phenyl is added to one carbon, and the OH ends up on the next carbon over. And then how do I go from the OH to the bromide? I use something like PBr3 to do a substitution. So in each case for our transformations, sometimes you see it right away and you can move forward and do your transformation, your multi-step synthesis with no problem. But by and large, the best approach you're going to have is going to be looking carefully at your product, identifying the functional groups in that product, and recalling what reactions you've seen that will give that functional group as a final result. And so in doing that retrosynthesis and working backwards a little, you can bridge that gap and find out how you can work forwards to this common structure and go forward from there. Okay, but a good synthesis is really about planning, and so that's why this retrosynthetic technique is going to be something that really pays off down the line.